This limitation wasn't just inconvenient, it was holding back the entire field of computing. Businesses wanted to use computers for accounting, inventory management, and data analysis, but the slow storage methods made these applications impractical. Scientists wanted to use computers to analyze experimental data and perform complex simulations, but they spent more time managing data storage than actually computing. The computer industry desperately needed a solution, a storage device that could hold large amounts of data and access any piece of that data almost instantly, without having to wade through everything else first. What they needed was random access storage. The challenge of creating such a device fell to a team of engineers at IBM's laboratory in San Jose, California. The leader of this team was Reynold B. Johnson, a remarkable figure in the history of computing who had already made significant contributions to data processing technology. Johnson was born in Minnesota in 1906 and had started his career as a high school teacher. But he was an inveterate tinkerer, always looking for ways to solve problems through engineering. In the 1930s, while still teaching, he had developed an electric test scoring machine that could automatically grade multiple-choice tests by detecting pencil marks on cards. This invention had caught the attention of IBM, and in 1934, they hired him and moved him to their research facilities. By the 1950s, Johnson was leading IBM's Advanced Systems Development Division in San Jose, California, and he had assembled a team of talented engineers to tackle the storage problem. Among them was a young engineer named Louis Stevens, whose expertise in mechanical engineering would prove crucial to the project. The team also included electrical engineers, physicists, and material scientists, a diverse group brought together by a common goal: to create a storage device that could hold millions of characters of data and access any piece of that data in a fraction of a second. The basic concept they settled on was elegant in its simplicity, even if the execution would prove devilishly difficult. They would create a series of rotating disks coated with magnetic material. Data would be stored on these disks by magnetizing tiny regions of the coating in different patterns. To read or write data, they would use electromagnetic heads that could move to any position on the disk, allowing them to access any piece of stored information almost instantly. In theory, it was straightforward. In practice, it would require solving dozens of engineering challenges that had never been tackled before.
Picture this. It's 1956, and a team of IBM engineers is standing nervously in a California laboratory, watching as a machine the size of 2 refrigerators hums to life. Inside this mechanical behemoth, 50 massive aluminum disks begin spinning at 1,200 revolutions per minute, while delicate read-write heads float just millionths of an inch above their surfaces. The tension in the room is palpable. One miscalculation, one vibration, one speck of dust in the wrong place, and months of painstaking work could be destroyed in an instant. But as the machine stabilizes and the first bits of data are successfully written and retrieved, these engineers realize they've just witnessed something extraordinary. They've created a device that can store 5 megabytes of information, roughly equivalent to 1 digital photograph by today's standards. But in 1956, this is nothing short of revolutionary. This 2-ton monster, officially known as the IBM 305 RAMAC, has just changed computing forever. This is the story of how the world's first hard drive was built and how it sparked a storage revolution that would eventually put terabytes of data in your pocket. To truly understand the magnitude of this achievement, we need to transport ourselves back to the early 1950s, to a world where computers were rare, room-sized behemoths that existed primarily in government facilities, universities, and the largest corporations. These machines were marvels of engineering, capable of performing calculations that would take human mathematicians weeks or months to complete. But they had a critical limitation that frustrated engineers and programmers alike: memory, or rather, the lack of it. The computers of the early 1950s relied primarily on two forms of data storage, and neither was particularly satisfactory. The first was magnetic core memory, a technology that used tiny magnetic rings threaded onto a grid of wires. Each ring could store a single bit of information by being magnetized in one direction or another. Core memory was relatively fast and reliable, but it was also expensive and limited in capacity. A typical computer might have only a few kilobytes of core memory, enough to hold a few pages of text, but nowhere near enough to store the vast data sets that businesses and researchers needed to work with. The second storage method was even more primitive: punched cards and magnetic tape. Punched cards, inherited from the pre-computer era of tabulating machines, were pieces of stiff paper with holes punched in specific patterns to represent data. They were cheap and relatively reliable, but accessing information stored on punched cards was agonizingly slow. To retrieve a specific piece of data, you had to physically sort through stacks of cards, a process that could take minutes or even hours. Magnetic tape was somewhat better. It could store more data in less physical space, but it suffered from the same fundamental problem. Tape was a sequential storage medium, meaning that to access data at the end of the tape, you had to wind through everything that came before it. It was like trying to find a specific song on a cassette tape. You had no choice but to fast forward or rewind until you found what you were looking for.
The first major challenge was the disks themselves. They needed to be perfectly flat and incredibly smooth, with a surface that could hold a stable magnetic coating. They also needed to be rigid enough to maintain their shape while spinning at high speeds, but not so heavy that the motors couldn't turn them efficiently. After experimenting with various materials and manufacturing techniques, the team settled on aluminum disks, each 2 feet in diameter and about 1/16 of an inch thick. These disks were machined to exacting tolerances and then coated with a thin layer of iron oxide, essentially the same magnetic material used on tape recorders, but applied in a way that created an extraordinarily smooth and uniform surface. Creating these disks was an exercise in precision manufacturing that pushed the limits of 1950s technology. The aluminum blanks had to be machined flat to within a few thousandths of an inch, then polished to a mirror finish. The magnetic coating had to be applied evenly, without any lumps, bubbles, or thin spots that could cause data errors. Even the smallest imperfection could be catastrophic. The team experimented with various coating methods, including spraying, dipping, and painting, before finally developing a technique that produced consistent results. They would spray the iron oxide mixture onto the spinning disc in a carefully controlled environment, creating a coating that was only a few millionths of an inch thick but remarkably uniform. But the discs were only part of the equation. The team also needed to develop the read-write heads that would actually store and retrieve data from these magnetic surfaces. These heads were small electromagnets that worked on the same basic principle as tape recorder heads. When writing data, an electrical current would flow through the head, creating a magnetic field that would magnetize a tiny spot on the disk surface. When reading data, the head would detect the magnetic field from previously magnetized spots and convert it back into an electrical signal. The revolutionary aspect of the RAMAC heads was that they needed to work while floating just barely above the surface of the spinning disk. This was necessary because the heads needed to be close enough to the magnetic coating to write and read data reliably, but they couldn't actually touch the surface, or the friction would damage both the head and the disk.
The solution the team developed was a phenomenon called an air bearing. As the disk spun at high speed, it would drag a thin layer of air along with it. By carefully shaping the read-write head, the engineers could make it fly on this cushion of air, maintaining a stable distance from the disk's surface. The distance they achieved seems almost absurd by modern standards. The heads flew approximately 6/1000ths of an inch above the disk surface. To put this in perspective, a human hair is about 3/1000ths of an inch thick, meaning the gap between the head and the disk was about twice the width of a human hair. This might not sound particularly impressive, but consider that this gap had to be maintained while the disk was spinning at 1200 RPM, while the head was moving back and forth across the disk surface, and while the entire machine was subject to building vibrations, temperature fluctuations, and other environmental factors. It was an extraordinary engineering achievement. Louis Stevens led the effort to design these flying heads, and it required countless hours of experimentation and calculation. The heads had to be light enough to respond quickly to the air cushion, but heavy enough to remain stable. They had to be shaped precisely to generate the right amount of lift from the moving air. And they had to be mounted on arms that could move them quickly and accurately to any position on the disk. The team built prototype after prototype, testing each one on spinning disk assemblies and making minute adjustments to the design. They studied the aerodynamics of the heads, the mechanics of the arm assemblies, and the dynamics of the entire system.
One of the most critical challenges was dealing with vibration. When you have a head flying a fraction of a hair's width above a spinning disk, even the tiniest vibration can cause a collision, an event the engineers called a head crash. A head crash could gouge the magnetic coating off the disk, destroying data and potentially damaging the head itself. The team had to design the entire system to minimize vibration from every possible source. The motors that spun the disks had to be perfectly balanced. The disk assemblies had to be mounted on vibration-isolating supports. Even the building's foundation had to be considered. The San Jose laboratory was deliberately located away from railroad tracks and busy roads to minimize external vibrations. The RAMAC ultimately used 50 disks, stacked on a vertical spindle like a tower of giant phonograph records. Each disk had magnetic coating on both sides, giving the system 100 recording surfaces in total. The disks were spaced about 3/4 of an inch apart, and between each pair of disks was an arm that could move in and out radially, carrying a read-write head that could access the upper surface of the lower disk or the lower surface of the upper disk. This meant the machine had 50 arms, each with 2 heads, for a total of 100 heads, one for each recording surface. The mechanical complexity of this system was staggering. All 50 disks had to spin in perfect synchronization on a single vertical shaft. The 50 arms had to move smoothly and independently, positioning their heads over specific tracks on the disks. A sophisticated control system had to coordinate all these movements, directing the right head to the right position at the right time. The engineering team had to design systems that could manage this complexity reliably, day after day, in an era when computer control systems were primitive by modern standards. The control electronics for RAMAC were built using vacuum tubes, the standard electronic components of the 1950s. Transistors existed by this time, but they were expensive and not yet reliable enough for critical applications. So the control system for RAMAC used hundreds of vacuum tubes, which generated substantial heat and required their own cooling systems. The machine had to monitor the position of all 50 arms continuously, using a feedback system that could detect where each arm was and move it to where it needed to be. This positioning system had to be accurate to within a few thousandths of an inch, a remarkable precision for mechanical systems of that era.
Data on the RAMAC disks was organized into tracks, concentric circles on each disk surface, like the grooves on a phonograph record, except these circles didn't spiral inward, but were separate rings at different radii. Each track could store a certain amount of data, and the tracks were numbered from the outer edge of the disk to the inner edge of the disk. To access a specific piece of data, the control system would first move the appropriate arm to position its head over the correct track. This movement was called a seek operation, and it took a variable amount of time depending on how far the arm had to move. Once the head was in position, the system would wait for the disk to rotate until the desired data passed under the head. This was called rotational latency. Then the data could be read or written.
The average time to access data on RAMAC was about 0.6 of a second, an eternity by modern standards where hard drives access data in milliseconds. But in 1956, this was revolutionary. Compared to magnetic tape, where accessing a specific piece of data might take several minutes, RAMAC was blazingly fast. And unlike core memory, which was limited and expensive, RAMAC could store 5 million characters of data, 5 megabytes in modern terminology. This capacity seems laughably small today when smartphones routinely have 128 or 256 gigabytes of storage. But in the context of 1950s computing, 5 megabytes was enormous. It was enough to hold the equivalent of 64,000 punched cards, or about 5 million characters of text. The physical size of the machine reflected the ambition of the project and the technological limitations of the era. The complete IBM 305 RAMAC system, which included the disk storage unit along with the computer and associated equipment, occupied about 150 square feet of floor space. The disk storage unit itself, officially designated the IBM 350 disk storage unit, was roughly the size of 2 modern refrigerators standing side by side. It stood about 5 feet tall, measured about 5 feet long and 3 feet wide, and weighed approximately 1 ton. When you added in the associated electronics and power supplies, the total weight approached 2 tons. Moving a RAMAC system was a major undertaking. IBM had to use special equipment to transport these machines to customer sites, and installing one required careful preparation. The floor had to be strong enough to support the weight, and the environment had to be controlled carefully. Temperature and humidity had to be kept within specific ranges because fluctuations could affect the dimensions of the components and cause the flying heads to crash into the disks. The machine required substantial electrical power and generated considerable heat, so adequate cooling and ventilation were essential. In many ways, installing a RAMAC system was more like installing a piece of industrial machinery than a computer peripheral. But despite its size, weight, and complexity, RAMAC was a commercial success almost from the moment IBM announced it. The company unveiled RAMAC to the public in September 1956 at a press conference that generated significant coverage in newspapers and industry publications. The demonstration was carefully choreographed to show off the machine's capabilities. IBM representatives would ask RAMAC to retrieve specific pieces of information from its vast storage: a customer record, an inventory item, a flight reservation, and within a second or two, the answer would appear on the computer's output device. To audiences accustomed to batch processing and long waits for data retrieval, this seemed almost magical. The first RAMAC system was delivered to Zellerbach Paper in San Francisco in June 1956, a few months before the public announcement. Zellerbach used it for inventory control, a perfect application for random access storage. The company's warehouses held thousands of different paper products, and tracking inventory using traditional methods was time-consuming and error-prone. With RAMAC, warehouse workers could instantly check inventory levels, update records when shipments arrived or departed, and generate reports on demand. The system transformed their operations and demonstrated the practical value of random access storage.
Other early customers included United Airlines, which used RAMAC for flight reservations, and several banks, which used it for account management. These applications had something in common. They all required rapid access to specific pieces of information from large data sets. They all involve situations where sequential storage methods like tape or punched cards were impractical because the data needed to be accessed in unpredictable orders. RAMAC made these applications feasible for the first time. IBM initially offered RAMAC as a lease-only product, as was common for computer equipment at that time. The monthly lease payment was approximately $3,200, equivalent to roughly $35,000 in today's money. This might seem expensive, but for companies that could utilize the system effectively, it was a worthwhile investment. The alternative, employing large staffs of clerks to manage data manually, or spending hours waiting for sequential storage systems to retrieve information, was often more expensive in the long run. The technology behind RAMAC was so novel that IBM filed numerous patents covering various aspects of the system. Reynold Johnson and his team members' names appeared on dozens of patents related to disk storage, covering everything from the flying head design to the disk coding methods to the mechanical arm positioning systems. These patents would prove valuable to IBM for decades, as the entire hard disk drive industry evolved from the foundation that RAMAC established. But perhaps more important than the patents was the knowledge and expertise that the San Jose team developed during the RAMAC project. Building RAMAC had required pushing the boundaries of precision manufacturing, aerodynamics, magnetic materials science, and mechanical engineering. The team had learned how to make disks flatter and smoother than anyone had before. They had learned how to create magnetic coatings with unprecedented uniformity. They had learned how to make mechanical systems work reliably at tolerances measured in millionths of an inch. All of this knowledge would prove invaluable as IBM and other companies worked to improve and miniaturize hard disk technology in the years that followed. The success of RAMAC sparked rapid development in disk storage technology. Almost immediately after RAMAC's introduction, engineers at IBM and other companies began working on improvements. The first obvious target was capacity. 5 megabytes was impressive for 1956, but it wasn't enough for many applications. Engineers knew that they could increase capacity by packing data more densely on the disk surfaces, storing more bits per square inch. This required several improvements: better magnetic coatings that could hold smaller magnetized regions, better read-write heads that could detect weaker magnetic signals, and better positioning systems that could place the heads more precisely over narrower tracks.
The second target was speed. While RAMAC was fast compared to tape and punched cards, engineers knew they could do better. Faster disk rotation would reduce rotational latency. Faster arm movement would reduce seek times. Better electronics would reduce the overhead time needed to process data. Each of these improvements required additional engineering work, but the payoff would be systems that could access and transfer data more quickly. The third target was size and weight. A 2-ton machine was acceptable for a large corporation with a dedicated computer room, but it made disk storage impractical for smaller organizations or for applications where space was limited. Engineers began exploring ways to make disk drives more compact. Smaller disks would reduce weight and size, though they would also reduce capacity, unless the data density could be increased proportionally. Better materials and more efficient designs could reduce the weight of the mechanical components. Solid-state electronics, transistors instead of vacuum tubes, could reduce the size and heat output of the control systems. Progress came quickly. In 1961, just 5 years after RAMAC, IBM introduced the 1301 disk storage unit. The 1301 used disks that were 25 inches in diameter, slightly larger than RAMAC's 24-inch disks, but it achieved a storage density that was 6 times higher. Instead of 5 megabytes, the 1301 could store 28 megabytes. It was also faster, with an average access time of about 80 milliseconds, compared to RAMAC's 600 milliseconds. The improvements came from better magnetic coatings, improved head designs, and more sophisticated electronics. In 1962, IBM introduced another innovation, the removable disk pack. The IBM 1311 disk storage drive used disk packs that could be removed from the drive and replaced with different packs, similar to how you might change a tape on a tape recorder. Each pack contained 6 14-inch diameter disks and could store about 2 megabytes of data. While this was less than RAMAC's capacity, the removable pack concept offered a crucial advantage. You could have unlimited storage capacity by using multiple packs, swapping them in and out as needed. The disk packs were sealed in protective covers when removed from the drive, making them portable and relatively easy to store. This concept would become standard in the disk drive industry for many years. The pace of improvement in disk storage technology was remarkable. Capacity grew exponentially, roughly doubling every 2 years, a trend that would continue for decades. Access times fell steadily as motors spun faster and positioning systems became quicker. Size and cost decreased as manufacturing techniques improved and economies of scale kicked in. By the late 1960s, disk storage had become standard on most mainframe computer systems, and the technology was beginning to appear in the mini-computers that were starting to challenge mainframes for certain applications.
The engineering principles established by the RAMAC team, magnetic disks, flying heads, ARM positioning systems, random access organization, remained fundamental to disk storage technology even as the specific implementations evolved. Throughout the 1970s and 1980s, as the computer industry exploded with the introduction of personal computers, disk drive technology continued to advance at a breathtaking pace. The 5.25-inch floppy disk drive, introduced in 1976, brought disk storage to early personal computers, though with capacities measured in hundreds of kilobytes rather than megabytes. The first hard drives designed specifically for personal computers appeared in the early 1980s with 5 megabyte and 10 megabyte drives that seemed enormous at the time, but that would be hopelessly inadequate within just a few years. Reynold Johnson, the leader of the RAMAC project, continued working in the computer industry for many years after RAMAC's success. He received numerous awards and honors for his contributions to computing technology, including the National Medal of Technology, which President Reagan presented to him in 1986. He lived to see disk storage technology evolve from the 2-ton RAMAC to hard drives smaller than a deck of cards that could store thousands of times more data. He passed away in 1998 at the age of 92, having witnessed the entire transformation of the storage industry that he had helped launch. The site of the original RAMAC development, the IBM San Jose laboratory, became the heart of IBM's disk drive operations. For decades, San Jose was where IBM developed its most advanced disk drive technologies, and the region around San Jose evolved into what we now know as Silicon Valley. While Silicon Valley is famous today for semiconductor manufacturing and software development, it's worth remembering that storage technology played a crucial role in the region's early development. The expertise in precision manufacturing, material science, and electromechanical systems that IBM cultivated in San Jose helped create the industrial base that would support the broader high-tech industry. Today, hard disk drive technology has evolved to a point that would have seemed impossible to the RAMAC team. Modern hard drives store multiple terabytes of data on disks just a few inches in diameter. The fly height of the read-write heads has decreased from RAMAC's 0.006 of an inch to just nanometers, literally atomic scale distances. The data density has increased by a factor of many billions. A modern smartphone contains more storage capacity than all the RAMAC systems that IBM ever built, combined multiplied by a factor of thousands. And yet, the fundamental principles remain the same: rotating magnetic disks, flying heads, random access organization.
The impact of RAMAC and its descendants on modern society is difficult to overstate. Random access storage made possible the computer revolution of the late 20th and 21st centuries. Without the ability to store and quickly retrieve large amounts of data, most of the applications we take for granted today simply wouldn't exist. Online shopping requires databases that can instantly access product information and customer records. Social media requires storage systems that can retrieve photos and posts from among billions of items. Streaming video requires storage systems that can serve up movies and TV shows on demand. Even email, one of the most basic internet applications, depends on storage systems that can quickly locate specific messages among millions or billions.
Beyond the direct impact of disk storage technology, RAMAC demonstrated something important about innovation and engineering. The RAMAC team succeeded not because they made a single breakthrough, but because they solved dozens of difficult problems and integrated the solutions into a working system. They advanced the state-of-the-art in precision machining, magnetic materials, aerodynamics, mechanical design, and control systems. They showed that complex engineering challenges could be overcome through systematic experimentation, careful measurement, and iterative improvement. This approach, tackling big problems by breaking them into smaller, manageable pieces and then integrating the solutions, became a model for engineering projects throughout the computer industry. The RAMAC story also illustrates the importance of corporate research and development in driving technological progress. IBM invested significant resources in the San Jose laboratory and gave Reynolds Johnson's team the time and freedom to work on what was essentially a speculative project. There was no guarantee that RAMAC would succeed, and even if it did, there was no certainty that customers would want to lease such an expensive, complex system. But IBM management understood that computing technology needed better storage solutions, and they were willing to invest in finding those solutions. This kind of long-term, fundamental research became increasingly rare in later decades as companies focused more on short-term returns, but it was crucial to the development of many foundational technologies. The legacy of RAMAC extends beyond technology into the realm of historical preservation and education. IBM donated one of the original RAMAC systems to the Computer History Museum in Mountain View, California, where it remains on display. This machine, or one very much like it, was the great-grandfather of the storage devices in every computer, smartphone, and data center in the world. Visitors to the museum can see this massive machine and try to imagine the San Jose laboratory in 1956, with Reynolds Johnson and his team watching nervously as their creation hummed to life for the first time. Looking at RAMAC today, with its massive disks and vacuum tube electronics, it's easy to see it as a relic, a primitive ancestor of modern technology. But this view misses something important. RAMAC wasn't primitive. It was state-of-the-art. It represented the absolute pinnacle of 1950s engineering. The people who built it weren't working with crude tools and rough approximations. They were using the most precise manufacturing techniques available, the most advanced materials, the most sophisticated control systems. They were pushing the boundaries of what was possible with the technology of their time, and they succeeded brilliantly. The story of RAMAC is ultimately a story about human ingenuity and the power of engineering to transform the world. A team of engineers saw a problem, the lack of fast, high-capacity storage for computers, and they set out to solve it. They didn't have a roadmap. Nobody had built anything like RAMAC before. They had to figure out, through experimentation and analysis, how to make disks smooth enough, how to make heads fly close enough, how to make positioning systems accurate enough. They had to invent manufacturing techniques and develop new materials. They had to build prototypes, test them, learn from the failures, and iterate toward success.
And when they succeeded, they changed computing forever. They made possible applications that nobody had imagined when they started the project.
They created an industry that would employ millions of people and generate trillions of dollars in economic value over the following decades. They laid the groundwork for the information age, for the digital revolution that would transform every aspect of human society. The 2-ton device that Reynold Johnson and his team built in that San Jose laboratory in 1956 was more than just a machine. It was a glimpse of the future, a demonstration of what would become possible when data could be stored and accessed at will. It was the beginning of the storage boom that would eventually put the entire knowledge of humanity into devices we carry in our pockets. And it all started with 50 spinning aluminum discs, 100 flying heads, and a team of engineers who refused to accept that something couldn't be done. The development of RAMAC didn't happen in isolation, and understanding the broader context of the 1950s computer industry helps illuminate why this achievement was so significant. In the years following World War II, the computer industry was in its infancy, dominated by a handful of companies and serving a tiny market of government agencies, research institutions, and the largest corporations. IBM was the undisputed leader in data processing, but even IBM's computers were rare and exotic machines. The company had built its business on punched card tabulators, electromechanical machines that could sort and process data encoded on cards. And the transition to electronic computers represented both an enormous opportunity and a significant risk. The RAMAC project emerged from this transitional period. IBM's leadership recognized that electronic computers would eventually replace punched card systems for many applications, but they also understood that computers needed better ways to store and access data. The punched card systems had one significant advantage. They allowed operators to access any card in a deck directly, without having to process all the preceding cards. This random access capability was essential for many business applications. If electronic computers couldn't match this capability, they would be less useful than the older punched card systems for certain tasks. Reynold Johnson understood this challenge intimately because his background was in punched card technology. His test scoring machine from the 1930s had been a punched card system, and he had spent years working on various improvements to IBM's card processing equipment. He knew what customers needed from data storage systems because he had seen how they used punched cards. This practical experience informed the RAMAC project from the beginning. Johnson and his team weren't just trying to build an interesting technical demonstration. They were trying to create a product that would solve real problems for real customers.
The decision to use magnetic recording as the basis for RAMAC was not obvious at the time. Magnetic recording technology existed in the 1950s, primarily in the form of tape recorders for audio and, increasingly, for computer data. But magnetic disk recording for data storage was essentially unproven. The team had to figure out whether the fundamental physics would even work. Could you magnetize spots on a spinning disk precisely enough to store reliable data? Could you read those magnetized spots accurately while the disk was moving? Would the magnetic signals be strong enough and stable enough to be useful? These weren't purely theoretical questions. The team built experimental rigs to test the basic concepts. They coated metal plates with magnetic material and spun them on motors, then tried to write and read data using prototype heads. These early experiments were crude, and many of them failed. The magnetic coatings flaked off. The heads skipped and bounced across the disk surfaces. The signals were weak and noisy. But each failure taught the team something, and gradually they refined their approach. They learned which magnetic materials worked best. They learned how to apply coatings that would stick to the disk and remain smooth. They learned how to shape the heads so they would fly stably above the disk surface. One of the most critical insights came from studying the aerodynamics of the flying heads. Louis Stevens, who led this aspect of the project, realized that the heads needed to be shaped like tiny airplane wings. As the disk moved beneath the head,
it would drag air along with it, and this moving air would flow over the curved surface of the head, creating lift. The amount of lift depended on the shape of the head, the speed of the disk, and the viscosity of the air. Stevens and his colleagues used equations from aeronautical engineering to calculate the expected flying height for different head designs, then built prototypes and measured their actual performance. The process was painstaking because they were working at such small scales. Measuring a gap of a few thousandths of an inch required special instruments and careful technique. The team also had to solve the problem of how to move the heads to different positions on the disk. The initial concept called for each head to be mounted on an arm that could swing in and out, like a phonograph cone arm. But coordinating the movement to 50 independent arms proved too complex. The team experimented with various mechanisms before settling on a design where all the arms on one side of the disk stack moved together as a unit. This reduced the number of independent moving parts, but required more sophisticated control logic to ensure that the correct head was selected for any given operation. The control system for RAMAC was a significant engineering challenge in its own right. The system had to keep track of where each arm was positioned, move arms to new positions when needed, select the correct head from among the 100 available, and coordinate all these operations with the timing of the spinning disks. Remember, this was 1956, before the invention of the integrated circuit or the microprocessor. The control system used relays, vacuum tubes, and other discrete components wired together into complex circuits. Debugging these circuits was difficult because there were no modern diagnostic tools. Engineers had to trace signals through the circuits using oscilloscopes and voltmeters, looking for problems one component at a time.
The software that controlled RAMAC was equally primitive by modern standards, though calling it software is somewhat anachronistic. The IBM 305 RAMAC system included a computer processor that ran programs, but these programs were quite different from modern software. They were written in machine language, direct instructions to the processor in the form of numeric codes, or in assembly language, a slightly more human-readable format that still required programmers to specify every detail of what the processor should do. There were no high-level programming languages for business applications, no databases management systems, no operating systems in the modern sense. Programmers had to handle every aspect of data storage and retrieval themselves, including managing the directory of where data was stored on the disks and handling errors when the hardware malfunctioned. Despite these limitations, or perhaps because of them, the programmers who worked with RAMAC developed sophisticated techniques for organizing and accessing data. They created index systems that allowed programs to find specific records quickly. They developed methods for handling situations where data needed to be updated, ensuring that the updated information was written back to the disk reliably. They created backup and recovery procedures to protect against data loss. Many of these techniques would later be formalized and incorporated into database management systems. But in the RAMAC era, every programming team had to invent their own solutions. The manufacturing process for RAMAC systems was as complex as the design. Each disk had to be machined and coded with extraordinary precision, and this precision had to be maintained not just for one disk, but for 50 disks in each system, and for multiple systems as production ramped up. IBM established specialized manufacturing facilities where skilled technicians performed the critical operations. The disk coding process in particular required careful control of environmental conditions. Temperature, humidity, and airborne particles all affected the quality of the coding. IBM built clean rooms, rooms with filtered air and controlled conditions, specifically for coding RAMAC disks. This was cutting-edge manufacturing technology for the 1950s. Quality control was paramount. Every disk was inspected and tested before it was installed in a system. Every read-write head was tested to ensure it would fly at the correct height and produce signals of adequate strength. Every ARM assembly was checked for smooth movement and accurate positioning. And once a complete RAMAC system was assembled, it underwent extensive testing before being shipped to a customer. IBM couldn't afford to have systems fail in the field, both because repairs would be expensive and because the company's reputation depended on reliability. The company invested heavily in testing equipment and procedures to catch problems before systems left the factory. Even with rigorous quality control, some systems did experience problems in the field. The flying heads, operating at such small clearances above the disk surfaces, were vulnerable to damage from any contamination. A particle of dust or a fleck of the magnetic coating could cause a head crash, destroying data and potentially damaging the disk. IBM developed procedures for cleaning and maintaining RAMAC systems, and the company employed field service engineers who were specially trained to work on this complex equipment. These field engineers became experts in diagnosing and fixing problems, and their feedback helped IBM improve subsequent generations of disk drives.
The customers who adopted RAMAC early were pioneers in their own right. They had to figure out how to integrate this new technology into their operations, how to write programs that could take advantage of random access storage, and how to justify the significant expense. The success stories from these early adopters helped convince other companies to try the technology. United Airlines, for example, used RAMAC to create one of the first computerized reservation systems. Before RAMAC, making a flight reservation required telephone calls between travel agents and airline offices, with agents checking paper records to see which flights had available seats. With RAMAC, seat availability could be checked instantly, and reservations could be recorded immediately. This dramatically improved the efficiency of the reservation process and provided better service to customers. Banks found similar benefits. Before RAMAC, checking an account balance or posting a transaction required locating the customer's ledger card and manually recording the information. With RAMAC, account records could be accessed instantly from any teller station, and transactions could be recorded in real time. This made banks more efficient and reduced errors. It also enabled new services. For example, banks could now tell customers their current balance instantly, something that had been impractical with manual record keeping because the balance might have changed since the last time the ledger was updated. Manufacturing companies used RAMAC for inventory control and production scheduling. Before RAMAC, tracking inventory meant maintaining card files or paper records that had to be updated manually, a process that was slow and error-prone. With RAMAC, inventory levels could be updated as materials were received or used, and accurate inventory reports could be generated on demand. Production schedulers could check material availability instantly and adjust schedules accordingly. This improved efficiency and reduced waste. These success stories demonstrated that RAMAC wasn't just a technical achievement. It was a practical tool that could transform business operations. IBM's sales force used these examples to convince other potential customers to adopt the technology. And gradually, RAMAC systems spread through the business world. By the time production ended in 1961, IBM had installed approximately 1,000 RAMAC systems, a small number by today's standards, but significant for such an expensive and specialized piece of equipment. The financial success of RAMAC vindicated IBM's investment in the technology and encouraged the company to continue developing improved disk storage systems. But the impact went beyond IBM's bottom line. RAMAC proved that random access storage was not just theoretically possible, but practically achievable and commercially viable. This opened up a new direction for computer development. Engineers at other companies took note of IBM's success and began working on their own disk storage systems. Some of these efforts led to innovations that would push the technology forward in new directions.
One important area of innovation was in the physical size of the disks. While IBM's early systems used large disks, 24 inches in diameter for RAMAC, 25 inches for the 1301, engineers realized that smaller disks offered certain advantages. Smaller disks could spin faster because the outer edge didn't have to move as fast in absolute terms to achieve a given rotational speed. This meant lower rotational latency and faster data access. Smaller disks were also lighter, which made the ARM positioning systems easier to build and allowed faster seek times. And smaller disks meant smaller, more compact drive units that would fit into smaller spaces. The trend towards smaller disks accelerated through the 1960s and 1970s. IBM introduced 14-inch disk packs with the 1311 in 1962, as mentioned earlier. In 1973, IBM introduced the 3340 disk drive, which used 14-inch disks in a sealed assembly that IBM called the Winchester architecture. The Winchester drive was a breakthrough because sealing the disks and heads together in a contamination-free environment allowed much smaller flying heights and thus much higher data densities. The Winchester architecture became the standard for hard disk drives and remains the basis for modern drives. But the shrinking didn't stop at 14 inches. In the late 1970s and early 1980s, several companies developed 8-inch disk drives, primarily for the emerging mini-computer market. Shugart Associates, founded by IBM veteran Alan Shugart, was particularly important in this development. Then came 5.25-inch drives, initially as floppy disk drives, but later as hard drives. Seagate Technology, founded by Shugart and others in 1979, introduced the first 5.25-inch hard disk drive in 1980, the ST506, as it was called. It had a capacity of just 5 megabytes, the same as RAMAC, but in a package that weighed pounds instead of tons and cost hundreds of dollars instead of thousands. The ST506 and similar drives made hard disk storage practical for personal computers, which were just becoming popular in the early 1980s. The original IBM PC, introduced in 1981, used floppy disks for storage, but within a few years, hard drives became standard equipment. As PC sales exploded through the 1980s and 1990s, the market for small hard drives grew enormously, driving continued improvements in capacity, speed, and cost. Competition intensified as more companies entered the market, and the pace of innovation accelerated. The improvements came from advances in every aspect of the technology. Better magnetic materials allowed higher recording densities. Better head designs allowed smaller flying heights and better signal quality. Better servo systems, the mechanisms that position the heads over the tracks, allowed narrower tracks and thus more data per disk surface. Better signal processing electronics allowed more reliable detection of weaker signals, and better manufacturing techniques allowed all of these improvements to be produced at lower cost and higher quality.
One particularly important innovation was the development of thin film heads in the 1970s and 1980s. The original RAMAC heads were wound coils of wire around a magnetic core, similar to the heads used in tape recorders. These worked, but they were relatively large and limited in performance. Thin film heads, by contrast, were made using photolithographic techniques borrowed from semiconductor manufacturing. Thin layers of magnetic and conductive materials were deposited on a substrate, then patterned to create tiny magnetic circuits. These thin film heads were much smaller than wound heads, allowing them to work with narrower tracks and higher data densities. They also had better high-frequency response, allowing faster data transfer rates. Another crucial innovation was the development of magnetoresistive, or MR, read heads in the 1990s. Traditional heads used the same magnetic element for both reading and writing, but MR heads used a separate element for reading. This element changed its electrical resistance in response to magnetic fields, allowing much more sensitive detection of the weak magnetic signals from high-density recordings. MR heads enabled another leap forward in recording density, and they were followed by even more advanced technologies like giant magnetoresistive heads and tunnel magnetoresistive heads, each generation enabling higher densities. The flying height of the heads continued to decrease as the technology advanced. RAMAC's heads flew about 6,000 nanometers above the disk surface. By the 1990s, flying heights had decreased to hundreds of nanometers. By the 2000s, they were in the tens of nanometers. Modern hard drives operate with flying heights around 3 to 5 nanometers, just a few dozen atoms. At these distances, the heads aren't really flying on an air cushion in the traditional sense. They're close enough that molecular forces become significant. Maintaining stable operation at these distances requires extraordinary precision in manufacturing and sophisticated control systems that can adjust the flying height dynamically in response to changing conditions. The evolution of disk drive technology also involved changes in the magnetic recording method itself. RAMAC used what's called longitudinal recording, where the magnetized regions on the disk are oriented parallel to the disk surface, pointing either clockwise or counterclockwise around the track. This worked well for low to moderate recording densities, but as engineers tried to pack data more densely, they ran into fundamental physical limits. When magnetized regions become too small, they become thermally unstable. Thermal energy from the environment can spontaneously flip the magnetization, destroying data. To overcome this limit, engineers developed perpendicular recording, where the magnetized regions are oriented perpendicular to the disk surface, pointing either up or down. Perpendicular recording allows higher recording densities for complex physical reasons related to how magnetic fields interact with the recording medium. The transition to perpendicular recording in the mid-2000s enabled another jump in hard drive capacities from hundreds of gigabytes to multiple terabytes. More recently, hard drive manufacturers have developed technologies like shingled magnetic recording, or SMR, and heat-assisted magnetic recording, or HAMR, to push densities even higher. SMR works by overlapping adjacent tracks, similar to how shingles on a roof overlap. This allows narrower effective track widths and thus higher densities, though it complicates the process of writing data because writing to one track partially overwrites the adjacent track. HAMR uses a laser to heat tiny spots on the disk immediately before writing, temporarily making the magnetic material easier to magnetize. This allows the use of magnetic materials that are more thermally stable, enabling even higher recording densities. Each of these innovations required solving new engineering challenges. Perpendicular recording required new head designs and new recording media. SMR required new control algorithms and firmware. HAMR required integrating tiny lasers into the read-write heads and developing recording media that could withstand repeated heating and cooling cycles. The history of hard drive technology is a story of continuous problem-solving, with each generation of engineers building on the work of their predecessors while pushing the technology in new directions. The improvements in hard drive technology over the decades are staggering when quantified. Storage capacity has increased by a factor of roughly 50 million since RAMAC. A modern 20 terabyte hard drive stores 4 million times as much data as RAMAC in a package that weighs about a pound instead of a ton. The cost per megabyte of storage has decreased by a factor of several million. Access times have decreased by a factor of several hundred. Data transfer rates have increased by factors of millions. These improvements have compounded over more than 60 years, representing one of the most sustained and dramatic technological progressions in any field. This progress didn't happen automatically. It required continuous investment in research and development by companies across the disk drive industry. It required advances in related fields like material science, nanotechnology, and control systems. It required feedback from customers about what they needed and what problems needed solving. And it required the kind of engineering persistence that characterized the original RAMAC project. The willingness to tackle difficult problems, to experiment until solutions emerged, to learn from failures and iterate toward success. The economic impact of the disk drive industry has been enormous. At its peak in the 1990s, the industry employed hundreds of thousands of people worldwide and generated tens of billions of dollars in annual revenue. The industry has consolidated significantly since then, with most production now concentrated in a few large companies, but hard drives remain essential components in data centers, personal computers, and many other applications. The cumulative value of all the hard drives produced since RAMAC numbers in the trillions of dollars. But beyond the direct economic impact, hard drives have been enablers of the broader digital revolution. They made possible the personal computer industry by providing affordable storage for software and data. They made possible the Internet by providing the storage infrastructure for websites, email, and online services. They made possible digital media by providing a way to store music, photos, and videos. They made possible big data analytics by providing a way to store massive data sets for analysis. In each case, the ability to store large amounts of data affordably and access it quickly was a prerequisite for the application to exist. The competition between hard drives and other storage technologies has been an ongoing theme throughout this history. Solid-state drives, SSDs, which use semiconductor memory instead of magnetic disks, emerged as a serious alternative to hard drives in the 2000s. SSDs offer significant advantages. They're faster, more durable, no moving parts, quieter, and more power efficient. However, hard drives maintain advantages in capacity and cost per gigabyte. For applications where large amounts of storage are needed and cost is a primary concern, such as data centers storing archived data, hard drives remain the technology of choice.